Welcome to another lesson from Transparent Physics. In this lesson, I'm going to show you how to solve two different Kepler's third law problems, and between these two solutions should be all you need to solve any Kepler's third law problem you're facing. So let's get right at it. And again, we have our quip sheet, and today we got some jelly beans left over from Easter, so we'll go good, and good. All right, so there we go. I'm ready to go. Got my quips started and ready. So let's do this. Okay, so a geosynchronous satellite orbits the Earth once every 24 hours. By definition, that's what a geosynchronous satellite does. Those are handy for lots of purposes. Given that the Moon has an orbital period of 27.3 days and an average distance of 385,000 kilometers, what is the average distance of the satellite from the Earth? So our first step would be to read the question, which we have. We've got any Kepler's third law problem, you're going to want to be looking for two satellites orbiting a central mass, and we do definitely have that. So we got our question out of the way. All right. Next up, underline the important information. 24 hours. And we can start thinking about that's the satellite. So I'm going to call that TS. The Moon has an orbital period of 27.3 days. T-Moon. And an average distance of this, and we're going to call that RM for the orbital radius of the Moon. And we're looking for the average distance of the satellite from the Earth. So if this is TS and this is TM and this is RM, then this is going to be RS for satellite. Now the typical equation does show like TA and TB, but we don't need to use A and B. We can use whatever letters make sense for the scenario. So, all right, and we have underlined. Underlined. All right. Get our information in here. Jelly beans take longer to eat than you think they would. All right. So we have the Earth, and we have a satellite, and we have the Moon out here. And we know that the Earth to the Moon is 385,000 kilometers. We know the Earth to the satellite is our unknown. We also know that the orbital period of the Moon is 27.3 days. And the orbital period of the satellite is 24 hours. Now, right off the bat, we have to note that we can use any units we want to in Kepler's third law, but we cannot have different units. So we can't have days and hours in the same thing. So easy enough to change. We'll just make this into days, and we're good to go. Okay, and we've identified our unknown. We've got our known information. So I think we have identified our information. All right, next up is solving for the procedure. How are we going to get to the answer? That's a good one. Now, with Kepler's third law, there is only the one equation. I mean, there's Newton's version of it too, but if we go straight Kepler, we have T and R and squared and cubed and equals. And then you choose your letters. Here's my big brain tip for you. When you're deciding, it doesn't matter what you put on top, the ratio is going to work out either way. Just as long as you're consistent that you keep the same thing on the top on both fractions. Put your unknown in the top. It's going to save you a step when you're algebraically manipulating. So since satellite is the thing that we don't know, I'm going to put satellite on top, and then moon on the bottom. Okay, always put your unknown on the top of the fraction you're interested in. Now, I always like to manipulate for the unknown before we move in. And when we're doing this, we are looking for RS. So we want to get RS by itself. That being done, I'm going to rewrite this just so our unknown is on the right side of the formula. I always prefer to do that. And then this is TS and TM squared. Now, if you are getting rid of a cube, you can take what's known as the cube root. Okay, so RS over RM cubed. To get rid of the cube, take the cube root. Now the cube root is the same as saying TS over TM squared. Just like taking a square root is to the 1/2, taking a cube root is to the 1/3. And those two exponents can combine together to give us this. RS over RM equals TS over TM, all that to the 2/3 power. Now, I personally prefer to see it this way. I like to combine these exponents together so we don't have to work with them separately. So again, I want to get RS over RM out of that cube. So I take the cube root of both sides. Taking the cube root is the same as taking it to the 1/3 power. And then squared and 1/3 power combined together to 2/3. And then from there, it's just a sort of a hop, skip, and a jump to actually get our numbers to work out. So I'm just going to get RM and isolate it. So our orbital radius of the satellite is equal to RM times the quantity TS over TM to the 2/3 power. The orbital period of, or orbital radius of the moon is given in kilometers, so that's what our answer is going to end up in. That's fine with me. I don't care. Doesn't matter what our units are. And I don't need to do anything to that. That's just kilometers. Now this quantity here is going to be the orbital period of the satellite. That is, if you remember, we're just going to write that as 1 day. And this is 27.3 days. Now, I could have left the orbital period of the satellite in hours and converted the orbital period of the moon to hours, but ultimately it would end up being the same fraction, so go with whatever's easiest. Okay, so when you're typing this exponent in, I sort of, if I was typing this in, it would maybe look like 385,000 times, open parenthesis, 1 divided by 27.3, close parenthesis, caret, open parenthesis, 2 divided by 3. So this part right here is this guy right here. That's the 2/3 power. All right, order of operations will take over. And make sure that this exponent gets done at the appropriate time. So when I plug it in, let's see what we get. Oh, and you know what? That is the that's the setup, and I'm ready for another. I don't think I'm going to like this flavor, but we'll find out. I think this is like toothpaste down here. All right. All right. Just for giggles, I'm going to do this part first, and this part first, and then multiply by that guy over there. So 1 divided by 27.3 to the open parentheses 2 divided by 3 power. Okay. So basically, what's that's telling me is that our orbital radius for the satellite is going to be at about 11% the distance that the moon originally was. So that ends up being about 42,000, 400, I don't know, 60 or so. Let's run the rounding. Okay. So that is how far away a geosynchronous satellite needs to be. Now that's from the center of the Earth. That's not from the surface of the Earth. All orbital distances are taken center to center. Generally speaking, that's more than 3 Earth radii or Earth diameters. So it's pretty far away from the Earth. So if this is the Earth, you could fit another Earth and another Earth and another Earth, and then honestly part of another one almost before we sort of get to that satellite. So that's how far away that satellite's going to be from the Earth. It's a decent distance. And again, that's about 1/10 the distance to the Moon. The Moon would be pretty far out there still, but okay. And we circle our answer. We got a solution. Again, my suspicion is this is going to end up tasting like toothpaste, but let's give it a go here. It's a little better than I thought it was going to be. All right. That's problem number 1. I'm going to stop the camera real quick, and then we're going to move to problem number 2. Okay, and here we are for the second problem. In this case, our scenario is dealing with the solar system as a whole, but Kepler's law again scales. It can work with satellites around a planet, it can work with planets around a star, it can work with stars around a galactic center, if we're in like a spiral galaxy where it's orbiting around a central mass. The asteroid belt in our solar system is believed to be the remnants of a protoplanet, maybe more than one protoplanet, that failed to condense into a single planet due to the influence of Jupiter's gravity. Pretty massive, so it kept things destabilized there. If we assume the unrealized planet, we're going to call that planet Frank, by the way, would have orbited with an average distance of 2.8 astronomical units from the Sun, how long would it take to orbit the Sun in years? Now, this guy right here, astronomical unit, is just a way for us to talk about big distances in the solar system, where the Earth to the Sun is 1 AU, 1 astronomical unit. So we use the distance from the Earth to the Sun, average distance, as sort of a ruler to look at other things. Okay, so I believe we have read the question. Let's underline. This is going to be quick because they don't really give us a lot. This is the orbital radius of the missing planet. We're going to call that Frank. And we're looking for how long it would take to orbit. And that's going to be our period. But that's it. That's all they gave us. Not a lot to work with. So when you run into a problem like this, you have to realize that there's other stuff going on in the solar system as well. They only give us one of the planets in the solar system, and we need 2 planets in order to solve this out. But the advantage is we know about all the other planets. Well, we know about most of the other significant planets to the best of our current knowledge. So we can pick any planet we want to, and what better planet to pick than our own planet, the Earth. So even though this is not a lot to work with, it is what we've got, and we'll move on from there. In terms of our information, though, let's take a look. Here's our Sun. Here's Frank. And Frank's at a distance of 2.8 astronomical units. And we want to know what Frank's period is going to be. And that's in years. So we could choose any other planet we wanted to. Let's choose Earth. So Earth is going to be, by definition, let's say around here somewhere. This is Earth. Earth is by definition of an AU at 1 AU. So that's cool. And then we would also need to know the period of the Earth. And the period of the Earth is 1 year. So we aren't given the other information, but if we're not, let's just pick an easy set. So let's just go with those guys. Okay. We're still going to have to work with the equation. Now the equation is going to look a smidge different because I've got different letters here, but it's the same equation. Oh, well, hold on. All right, so we've got T and R and an equal sign and a parenthesis and a squared and a cubed. Now we just need to pick our letters. What always goes on the top? The unknown quantity. So in this case, Frank has our unknown associated with it. So Frank's on top, Earth's on the bottom. And now we need to manipulate for the period of planet Frank. Between the problem I just showed you and this problem, that's all that you're ever going to have to do with Kepler's third law. You're either going to solve it for the period or you're going to solve it for the radius. So in this case, we're going to solve it for the period. It's a similar, though not identical process. And I think we have all information and we're working towards the procedure now. So probably somewhere in here, I should have taken my I value because we've got all the information down now. That's like tangerine. How pleasant. All right. Same thing here. I want to get rid of the square root, or I want to get rid of the square by making it a square root. So I'm going to take TF over TE. Make sure that looks like an F there. Take the square root of this side then, RF over RE. Taking a square root is the same as taking something to the 1/2 power. And then 1/2 and to the 3rd power can combine together to give us RF over RE to the 3/2. Now again, this is not the only way to do it. I've just found it's the most efficient way as far as the calculator solution goes. Okay, so when it's all said and done, we're going to get Frank by himself. And again, notice because Frank's on the top, we don't have to do anything else. He's ready to go. Just move the period of the Earth over. If Frank was on the bottom, we would need to do another step at this point. And who wants to do another step? It's rhetorical. You don't have to answer that. RF over RE, 3/2. And that is our procedure. We're ready to go. We got it all manipulated. All right. Plug, chug. Now look at how nice this works out. What's the period of the Earth? 1 year. Orbital radius average of Frank is 2.8 AU. Orbital period of the Earth, 1.0 AU. AU. 3/2. So you can see Kepler's 3 law problems don't have to be like super duper crazy hard because this one basically disappears, and really when it's all said and done, we just have to take 2.8. Technically there's not, well, 2.8 AU divided by 1.0 AU to the 3/2 power. And again, that's in years. Astronomical units cancel out. So if I was typing this in, I would say 2.8 times the quantity, open parenthesis, caret, not times, caret, 3 divided by 2. Now again, you might be saying transparent physics, couldn't you just type in 1.5? And yeah, you could. I just want to be consistent on the solution protocols here. So, all right. So we don't have to do anything else. It's just 2.8 caret 3 divided by 2. And that tells us that if this planet Frank existed at that distance, which is again about 2 times out further than the Earth, Frank would have an orbital period of around 4.7 years or so. Okay. And that's how you do it. And time for a celebratory jelly bean. Oh, you guys didn't see that one. I was off camera. Maybe a little sip of tea to wash it down. All right. So, either way, you're going to be doing with one of these manipulations. You're going to either be solving for R. If you're solving for R, it's going to end up looking something like this guy, although your letters might change. Your subscripts might change, not the R's and the T's. Or you might be solving for T. And if you're solving for T, it's going to end up looking like this. And again, it's going to be pretty much the same every time, just your subscript's going to change. Other hints to remember when you're solving Kepler's third law problems is it doesn't matter the units that we chose. We can see here we had days and kilometers. Here we had years and astronomical units. That's both fine, as long as you're consistent within the fraction. You can't have a different value on the top of the fraction as the bottom of the fraction. The ratio is broken then. And that's about it. Again, it doesn't have to be hard. And when you're choosing units, choose units that make it easier for you to solve it. Yeah, there's no reason to go and convert everything to seconds. We're used to working with seconds in physics a lot. So I see a lot of kids, when they see a period, even if it's in years, they go and convert it to seconds because that's what they're used to. And again, in other physics problems, you do have to have it in seconds in order for it to work out. But in problems like Kepler's third law, where it's all sort of ratios, you can leave it any units you want to. So please don't convert to seconds unless it makes sense for that problem. And you can see if we choose our units correctly, you can really streamline your solution at the end. And then the only thing you have to worry about is taking care of these taking care of these exponential values. And again, it's always either going to be to the 3/2 power or to the 2/3 power. And you don't have to do it this way. That's my personal preference. I find when you're plugging into the calculator, it's a pretty efficient way to go about doing it. All right. I hope I've had the opportunity to make this sort of problem a little clearer for you on transparent physics.